Pierre-Simon de Laplace, one of the pioneering physicists of the 18th century, once proposed a thought experiment. A being with unlimited mathematical capabilities who offers, give me the positions and velocities of all the particles in the universe, and I will predict the future. Now, my PhD was in quantum physics, which has a few things to say about this notion, but I want to leave that aside for today, and instead talk about something vastly more complex than most quantum systems, predicting the weather next weekend. Now, a few degrees warmer, sun instead of clouds, and our choices shift from indoors to out, from plans made to plans remade. Forecasts aren't just data, they affect our daily choices, and they affect the functioning of countless systems woven into our lives. Whether it's aircraft avoiding turbulence or catching tailwinds to decrease fuel consumption, or power grid operators dealing with fluctuating demand and fluctuating supply from renewable energy sources. And the key thing in all of these cases is that it's not that easy to get it right. As the old adage goes, weather forecasts are wrong too often to depend on and right too often to ignore. But to understand why, we can go back to Laplace, because he lays it out quite well. Give me the positions and velocities. If you want to understand the future state of a system, you have to know its state in the present. And it's not enough to know that state locally either. As winds wrap around the planet, the data on the other side of the world affects our weather. Furthermore, it is a notoriously chaotic system, with small perturbations accumulating over time into big effects. After all, the term butterfly effect is literally coined in reference to meteorology. And so that means our observations also need to be accurate enough that the errors in those observations don't compound into nonsense. If a butterfly flapping its wings in Brazil affects our forecast, we can't misplace the butterfly. Now, fortunately, looking 1 week ahead, the butterfly doesn't matter. But collecting these observations is still no small challenge. Despite billions of dollars in annual expenditure, critical measurements are lacking. About 95% of the data right now comes from satellites, which do a tremendous job of consistent global monitoring, but not without limitations. If you're looking down at the world from space, it's very easy to see where the clouds are or measure their temperature. But what do you look for when you want to see the wind speed on a clear sky? Indeed, a World Bank and World Meteorological Organization report from a few years ago noted that the remaining 5% of observations collected directly inside Earth's atmosphere are responsible for a full quarter of the impact on forecast accuracy, and are also the place where they see the greatest potential for future improvement. When it comes to in-atmosphere measurements, a long-running gold standard is weather balloons. Over 1,000 are launched around the world every single day, collecting data above the launch site until they burst in the stratosphere. But only part of the world has the resources and infrastructure to conduct such launches. And most of the world doesn't even have land from which to launch. Put that all together, and a full 85% of the planet is lacking in those observations. We in the US run a comprehensive weather balloon network, but that's of little consolation to us here in California, because our weather blows in from the Pacific Ocean, one of the world's largest observational gaps. When this region was hit by heavy flooding about a year and a half ago, forecasts as little as 1 day out were predicting the rainfall would be just below the limits of our infrastructure. They were wrong by a factor of 2. Clearly, we have to fill this observational gap. Could we put sensors on planes? Well, we do, and the data has significant impact. But to oversimplify the problem, most planes fly where most planes fly. You get a wealth of data above the world's busiest airports and in major flight corridors. But if you're collecting low-altitude data over open ocean, something is going catastrophically wrong. And really, that highlights the problem. We as a species are very good at putting sensors in our pockets, our cities, the oceans, even in space. But the atmosphere is a place that we only visit, often at great expense, when we have something important to do. And if we want to fully monitor it, that has to change. We need to be able to create systems that can live in the atmosphere for months, even years at a time. The reason why I moved away from physics research and co-founded a company in the weather space is because we saw the opportunity to do precisely that. building off of some work that I started back as an undergraduate at Stanford on long-duration controllable balloon systems that are truly comfortable living and working inside of the atmosphere, no matter how cold, how dark, or how wet it gets. And we quickly realized that this technology allows for access to any point in the sky for a fraction of the cost and environmental impact of existing technologies. And now we're flying over 100 of these around the globe. And I do mean around. You can see the one highlighted here is on its third loop of the Northern Hemisphere, collecting atmospheric observations everywhere it goes. And to understand the impact of truly global data collection, put yourselves in the position of a government when a hurricane is bearing down on the coast. You have to understand where it will make landfall in order to evacuate everyone who's in danger without evacuating anyone who isn't, needlessly uprooting their lives and making them question whether to trust you next time around. In 2022, we flew a campaign collecting data on the oceanic winds that steer these storms. When that data was incorporated into the US operational weather model, national weather prediction researchers found that the trajectory error at the 6-day forecast decreased by almost 20%, averaged across the entire season. That was achieved with just a fraction of the observations that are being collected right now. Indeed, we're seeing an absolute explosion in the quantity of in-atmosphere data as a result of advances in electronics, communications, sensors, and materials technologies that allow us to build dedicated data collection systems, not limited by the ground infrastructure or the schedules of airlines, but by the capabilities of the technology itself, capabilities that are advancing rapidly. And so, with a wealth of new data, it should be easy to predict the future. Well, it would be until we ran headfirst into the reason why Laplace's notion was a thought experiment. There are far too many particles in the universe for you to possibly fit on a computer. And scoping down to just the atmosphere isn't much help. If you have enough memory to fit this in your attic somewhere, please let me know, or let someone know. But so, we can't track the particles individually, but okay, we can do fluid dynamics. We take the atmosphere, we slice it up into a 3-dimensional grid, and we model how air moves through points along that grid. And that's great, but we've just swept most of the complexity under the rug. How does a volume of air with 10 grams per meter cubed of snow interact with a neighboring volume with 20 grams per meter cubed of rain? Do you get more snow, more rain, hail? All of these physical processes are happening at a scale much smaller than the multiple kilometers of our grid. So our model will completely miss them unless we independently track all these variables and derive equations that govern how they evolve and interact. If you look inside the code for a weather model, you will find hundreds of lines doing precisely that, citing generations of meteorological research to quantify these parameters accurately enough that we can meaningfully model these effects, but also simply enough that we can efficiently compute them. Indeed, with all of these constraints, it's a massive testament to the skill and dedication of the meteorological community that we're able to make forecasts as accurate as they genuinely are. And then, a couple years ago, something interesting happened. Yes, it's transformer models. It turns out that the same math that can take a picture of your friend and turn them into an anime character when trained on a library of images can also be trained on the historical weather record to take a snapshot of the present and turn it into the future. And remarkably, despite having no prior knowledge of physics or meteorology, these models actually work. Remember the hurricane scenario we talked about? For some reason, deep learning models are really, really good at that. And this is without access to any additional information. Furthermore, it's worth noting that one of these models runs on a supercomputer, whereas the other can fit on a single gaming graphics card. Now, there's no strange magic going on here. At core, these are simply a different mathematical structure by which we can simplify the complexities of the atmosphere and then map them from present to future. But finding a different mathematical approach to a wickedly hard problem is no small thing, especially when just in the past 2 years, these models have gone from fascinating but mediocre to consistently beating the cutting edge of physics models across the majority of variables and situations. And this rapid advance promises far more than simply more accurate forecasts. With how good deep learning models are at ingesting and making sense of large quantities of data, we can think about tailoring them to specific applications. Consider forecasts for wind farm output that incorporate not just weather data, but historical and current electricity generation in order to better predict future generation and help our grid as a whole to adopt fluctuating renewables. Or seasonal agricultural forecasts that help guide crop selection and improve global food security. Furthermore, with this 100,000-fold improvement in compute efficiency, it opens the door to take advantage of all of the data being collected by sensors around us and putting all that together to produce hyperlocal forecasts that tell you the weather where you are right now and the predictions for that location, as opposed to making the predictions for the nearest airport 10 miles away. And in closing, I'd like to step back a little bit further, because we live our entire lives underneath Earth's atmosphere. And it's very easy to take for granted the ways in which we think about and interact with the weather. Consider that today, you can wake up, check your phone, and know exactly what to expect for the day. Whereas 30 years ago, even though forecasts existed, you would most likely just hope for the best and maybe grab a jacket and umbrella just in case. That transformation in how we think about weather happened as a result of easy access to information. Now imagine looking ahead what happens with easy access to automation. Thanks to advances in agentic AI, you now have the possibility as individuals, as businesses, and as governments to incorporate accurate weather forecasts into the operation of critical systems seamlessly and holistically to truly leverage this insight in a consistent manner. Thanks to new data sources enabled by advances in hardware and AI, we are on the verge of a transformation in the way that humanity as a whole feels and interacts with the weather. Being able to trust the forecast for next weekend is just the start. Thank you.